Welcome to Entangled Things, your quantum computing podcast, hosted by Patrick and Ciprian.
Ciprian, what's your interest in quantum computing?
Well, Patrick, the interest goes well back to my early years in computer science. Actually, I would rather define myself as being a failed physicist. When I was very, very young, I had two big areas that I loved a lot. One was computer science, the other one was quantum physics. So, as I was in my early 20s, I started to study quantum physics. Eventually, I ended up as a computer scientist, but still, that was one of my first scientific loves. So, I at that time, I didn't imagine that fast forward 20 years or something, we will be at a point where we will be discussing how quantum physics can be used to build actual quantum computers. It's a moment in time, it's a period in time that makes me like super excited and in the same time super interested, because now it seems that what once was a beautiful idea, wishful thinking, now it's on the path of becoming reality.
Cool. So the reason I'm mostly interested in it is because, as you know, my background's security. After I got out of the military, I've been doing pen testing and that kind of stuff for a long time. And I think this is the real thing that's going to change the spectrum, it's going to change the game, if you will. And we'll talk a lot in future episodes about how this affects security. I've also been a student of physics for a long time as a sideline. But I think this is also an opportunity for all of us, because I think this is the one buzzword in the computing world that we can see coming. I didn't predict big data or machine learning just before they broke out, but this one, we're definitely seeing it coming for 4 or more years down the line. So
Yeah,
first thing, oh, go ahead.
yeah, and the other thing that makes me very, very interested and excited is I know a lot of problems in classical computing that are simply unsolvable today. We simply do not have enough computing power to solve those problems. And quantum computers are the ones that provide this promise that we will be able, if not fully solve, but at least tackle in a much more efficient way those problems. So that makes me, again, very, very interesting and excited about quantum computing.
So let's dig into that, because the first question we want to address here is, why do we need quantum computing? What's your answer to that when somebody asks?
Well, the answer is basically related to what I've just said. We have this need of solving very, very complex problems that we just cannot solve using classical computing. And the example that I like to give is an example about a very, very simple simulation. Like, think about, you have a system of electrons that can take 40 positions, which means that the system has 2 at the power of 40 configurations, since each one of those positions can have or will not have an electron in that position. So you need to track the probabilities of 2 at the power of 40 configurations, which roughly gives you a need of around 130 gigabytes of memory. Now, imagine that instead of 40 electrons, you need to actually simulate systems that have a much higher number of electrons. The immediate question is, where do you need to do that? Well, think about materials science, for example, right? Now, the idea is that the requirements of memory to do it in a classical way are obviously exploding exponentially, to the point where if you would have slightly above 300 positions to simulate, the number of memory locations that you would need would exceed the total number of particles in the known universe. Does that make sense to you?
So it does. And this is one of the things that you've really captured my imagination with, because when we first started talking about this years ago, you gave this example. And what you're talking about is the ability to model material science and revolutionize chemistry in a way that classical computing hasn't been able to do. You're talking about being able to create a Kevlar or a nylon or a new material every 6 hours instead of every 6 years.
Yeah, yeah, exactly. If you think about the big problems humanity is facing today, I would argue that a large portion of those problems could be solved by inventing or identifying new materials. Think about agriculture and the good old problem of fertilizers. We're still using like a kindergarten like approach to create fertilizers. Think about space travel. We need to protect our spaceships, we need to protect our astronauts. And remember, we still haven't really left the protective shroud of Earth's magnetic field. So when we're thinking about traveling to Mars or even beyond, we will definitely need new materials, not to mention the elephant in the room, which is medicine. And the list can go on and on and on. So the capability of understanding the evolution of complex natural structures, and I'm referring here to molecules, in order to build new materials becomes critical not only for the evolution, but at some point, I dare to say, for the survival of the human species.
So that's very interesting for, the sci-fi geeks and everybody who thinks about those material science. But there's other applications. There's a lot of other problems that classical computers can't scale to meet that quantum is going to be able to solve. And so basically, we're talking about, we've all been very happy with our geometry, for example, 5,000 years ago. And we don't imagine what life will be like with an algebra. But once it's created, or a calculus, if you talk about later maths, it opens up a whole new world. So the analogy I might use is that classical computing is like an algebra or geometry, and calculus, which takes us to the next level, is what quantum computing could bring us. It could change the way we think about everything. One interesting note, there's a company out of Vancouver named Qubit, and they have been programming. We'll talk about programming quantum in later episodes. That's probably too much for the first episode. They've been programming problems using a quantum algorithm that's using a simulated quantum computer. So it's still silicon, it's still classical computing, but they're finding that even just reimagining the problem in a quantum paradigm gives them an 8% increase on efficiency. And that if once they get actual quantum computers behind the calculations, they see 100-fold increases in performance, in productivity. And so even if we don't get to quantum computers in the next years, it's worth paying attention to already. So I think that we understand the why now. Somebody listening to us is going to understand what the why is. What is it now? So you mentioned these positions and analogous to memory on a regular computer. What is quantum computing? How does it work?
Yeah, so think about, again, coming back to the example on the positions of electrons, and that is kind of part of a much more complex problem, as I said, of simulating or understanding processes in nature. And this observation leads to the fundamental vision that sits behind quantum computing. As like, what if we could find a way to turn this difficult problem into a huge opportunity? So if those quantum processes are so difficult to simulate with classical computing, what if we could build a computer that uses those quantum processes as the core of its functionality? So instead of relying on the classical computing processes, what if we could build computers that use that interaction of particles at the quantum level to perform computation? And that's kind of the core idea that led to everything that we know today collectively as the field of quantum computing. Does that make sense?
Yeah, the way I might explain it is we need a better bit. So a bit in classical computing is an on and off switch. It's either on or it's off. It's binary, and that's the basis of all classical computing. And it scales very well compared to an abacus or counting beads or whatever. But we've reached its limits. Now you've already pointed out problems that it can't solve. So how do we get a better bit? Well, the better bit would be a qubit, and the qubit is, or qubit, depending on how you say it, is a bit that has a value from 0 to 1. It's not either 0 or 1 in the truest sense. It's a probability between those two infinitely distanced values. And so that means one qubit can hold an infinite number of values, not just 0 and 1. It gets complicated after that. But that's the crux of it, is a quantum computer uses bits that are infinite in value instead of binary in value.
Yeah, and think about it as well like this. So with a classical computer, you will use silicon-based chips, and those silicon-based chips, they represent bits, as you said. A bit can have only two clear and distinct states, 0 or 1. And those silicon-based chips are running some physical processes that run at a level that it's high enough, far enough from the level of quantum physics that makes the measuring, the setting, and the keeping of those states quite easy to implement. Now, as opposed to a classical computer, a quantum computer will use quantum systems like atoms, ions, photons, electrons, and so forth. And the fundamental property of these systems embodied in the concept of a qubit is the fact that the state can be a superposition. And let's propose to our listener a very simple exercise of imagination. You're sitting in your living room, right? Turn your body and face all the way to the left and then all the way to the right. That's something very easy that you can do. Now, I challenge you to turn to your left and to your right at the same time. That is something that obviously in the current world of physics is impossible. But what's interesting and it's fascinating to me, right? That if you are a particle in the quantum world, then you actually can do that. As a matter of fact, there will be a probability that you are looking left and the probability that you are looking right. And obviously, the sum of those probabilities must be 1, but your state is going to be what we call a superposition. So instead of having two distinct states, the fundamental thing that makes a qubit so powerful is the fact that it can have an infinite number of states, as opposed to two states that a bit has. And building on that, we have already built the whole kind of logical structure that allows us to transform this into concepts related to computing.
So at this point, the casual listener should be have their head spinning, because this is heavy stuff. Superposition is a class that is taught at MIT and Caltech and some of the greatest institutions, and takes a long time, even for people with strong physics backgrounds, to get their head around. So we're going to come back to this. We're going to talk about it. There's lots of great videos online and YouTube. Fermilab has great videos, and there's a bunch of different videos on superposition. Superposition, I don't think, is well named. I understand it, but you almost have to understand it before the name helps. And that actually isn't very helpful.
It's kind of like a chicken and egg situation,
yes,
right?
Very much so. Very much so. It's once you understand superposition, the name makes sense. But before then, it just actually confuses things. I'm going to take a very quick stab at giving another another understanding of that. And that is when we dig down into the deep, dark secrets of molecular physics, physics at the atomic level, we found out that we are not allowed, for whatever reason, there's many different explanations for why that might be the reason, to know everything there is to know about a particle, a photon, a quark, etc. We can know its position, we can know its speed, but we can't know both to a precision at the same time. And so it's that uncertainty, the uncertainty principle comes into play, that we're using to make calculations and predictions. And it's amazing that they've basically taken lightning and put it in a bottle with this quantum computing. And so that leads to so if I accept everything we've said, why is it hard to build a quantum computer? Why don't we have them?
Well, there are two reasons for that. One is it's really hard to build a physical quantum computer, but we will get to that a little bit later in our discussion. The other one, though, is some kind of very interesting protection, if I may call it like this, that nature has in place when it comes to quantum phenomenon. So let me get back to this example with the exercise. Suppose I'm looking left and right, and I'm moving between left and right, and at some point you come into the same room and you try to take a picture of me exercising. So most probably, no matter how many pictures you take, you will kind of have me somewhere in the between, looking all the way to the left and all the way to the right. Now, if I'm now a quantum particle, some very interesting thing will happen. No matter how many pictures you take of me, you will always have me in those pictures, either looking to the left, totally to the left, or completely looking to the right.
Never in transition. Never a transition.
There will be not a single picture where I will be somewhere in between. Now, in quantum computing, the name for this is collapsing the superposition state. In other words, that qubit that can have a potential infinite states between 0 and 1, the moment you measure it, you will either get a 0 or a 1. And that's one of the things that makes designing algorithms and writing programs in quantum computing very, very hard. The analogy that I give to a lot of folks is, it's a little bit forced, but it's still good, I believe. Imagine working with a database, and the only type of operation that you are allowed to do is to write into the database. Whenever you read something from the database, you will always get one of two results. So the challenge is write a program that works with that database. It's pretty difficult, right?
Mm. Yes. So to take your analogy and bring it home, I think, if I wanted to know whether you were going to be facing right or left under a certain circumstance, maybe at the top of the hour, and I had reason to believe that you consistently are either facing right or left at the top of every hour, what I could do is I could take that measurement, but it's going to be either you're facing right or facing left. But if I take that measurement 100 times, and 70% of the time you're facing left and 30% of the time you're facing right, I can make the prediction that 70% certainty that left is the right answer. Left is the correct answer. And that's how quantum computing works currently, is they set up a circumstance, they make a prediction based on that calculation, and then they observe it not just once, but repeatedly to come up with a probability. It's kind of like facial recognition. Facial recognition doesn't work with certainties. If you show a facial recognition program a face, it gives you a percentage. Yeah, 97% that is Ciprian. Or it might, you might be wearing glasses and a hoodie, and it might say 30% it's Ciprian. But I still think it might be Ciprian, but I'm only 30% sure. That's the quantum way of calculating things, correct?
Yeah, yeah. Now imagine a common friend of us has a way to reset my position in the room, right? So imagine this. I'm in the room, and let's imagine that position is me looking 45 degrees to the left. So that friend comes into the room, sets me looking 45 degrees into the room, leaves the room. You come in and you take a picture. So as you said, you will either have me looking all the way to the left or all the way to the right. Now, imagine that we repeat this process, let's say 100 times or 1,000 times or 100,000 times. The more we repeat the process,
Better the precision.
The closer we will be to a split of 75 to 25, right? So you will see me probably out of 100,000 measurements, you will see me 75,000 times looking all the way to the left, 25,000 times looking all the way to the right. And actually, from a mathematical point of view, we would need to repeat this an infinite number of times to get that exact initial state that our common friend resets me to. And that's the core of why it's difficult to work and to understand at the end of the day quantum computing.
Yeah, there's also the aspect that we're dealing, a bit is very small, but it's enormous compared to a qubit, because a qubit is literally a single photon or a single particle. It's even a fractional particle in some cases. So one of the other problems is that if you add the heat of observation, the extra energy of just monitoring the situation, the temperatures that we're dealing with quantum computing are closer to absolute zero than the vacuum of space. So that actually is the biggest impediment to doing this, is how do you shine light on an electron so you can see what it's doing without overwhelming the electron? It's like trying to run a classical computer in an electromagnet.
Yeah, exactly. And then there are some other even more weird properties that add to the complexity. We will clearly cover them in subsequent episodes of our show. One of them, which I would like to just kind of introduce right now, is entanglement. Entanglement being probably one of the most mind-bending or puzzling phenomenon of quantum computing.
Hence the name of our podcast.
Exactly, right? There's a reason why the name of our podcast is Entangled Things. So it turns out that two or more quantum particles can become entangled. And by that, we mean they form like a single system where the state of each particle cannot be described independently from the state of other particles. And what's the really kind of mind-bending thing is that if you separate those particles with incredible distances, like even think about light years here, we cannot yet do that for obvious reasons, but even if you separate them with the distances in the order of light years, the effects of measurement will apply to entangled particles. So let's give a simpler example. If you have two entangled particles, you separate them, say, on two different continents. One is over here in my house in Europe. The other one is over there, Patrick, in your house in the United States. So what happens is if you measure the particle that it's at your house in the United States, as we said, the state will collapse and you will get a 0 or a 1. But what's unbelievable is that the moment you measure your particle and its state collapses, my particle state will also collapse, and I will get a 0 or a 1. By the way, that this phenomenon is one of the things that puzzled Einstein for a long time. He had a really hard time grasping the fact that this is actually how entangled particles work.
Well, it made him question the entire thing of it made him hate quantum mechanics. He thought that how did he call it? He said spooky action at a distance. And,
yeah, that's one of his kind of known quotes.
Well,
the other one is related to Heisenberg's principle of uncertainty, right? And Einstein is known as saying, yeah, God does not play dice, right?
Right, but those are the principles that we're counting on for this. Those are the principles that power all this. Well, we're coming to a point where we've touched on a lot of the high level stuff, but who are the players? Let's talk about the people who are actually putting this together. We have to first acknowledge that the governments of the world, China, the United States, probably Russia, behind the scenes are playing, and in some cases not behind the scenes. China's acknowledged that they're working on quantum communications with a satellite, and there's been recent articles about successes in quantum communications where they've been able to communicate instantly over 27 miles, those kinds of things. But let's talk about the major players. Who do you think are the biggest players of note in building the first quantum computers?
So there are two categories of players here. There are players who aim to build the actual quantum processors, and those players can be further divided into the ones that attempt to build what we call circuit-based quantum processors, or in other words, universal quantum computers. And by the way, a universal quantum computer would be a computer that will allow you to actually implement, using it, any quantum computing algorithm. And then the other category is the ones that are building the so-called annealing quantum processors, which are dealing with a much more limited applicability and scenario. So these are what I call the builders, right?
And they muddy the water quite a bit. Somebody who's just trying to pay attention to this out of the corner of their eye would hear conflicting reports. They might hear that IBM has a 53 qubit system, and that's a breakthrough. And then, but a week before or a month before, hear that T-Wave has a 2000 qubit system. And it's not apples to apples. They're not doing the same thing.
No, they are not. So the big game is building the circuit-based quantum processor, or the universal quantum computing. And here you have players like, you mentioned IBM, you have Google, you have some of the Chinese, like the University of Science and Technology of China, USTC. And you have a quite interesting startup, which is Rigetti. And these are attempting to build using what I like to call the easier path. So they're either using photonics or superconductors. Now, there is a distinct player in this group, which is Microsoft. And Microsoft is attempting to build a quantum computer, a universal quantum computer, using a radically different approach, which is called topological quantum computing, which actually, without getting into the very complex details, uses properties of matter when matter is close to absolute zero, which is 0 Kelvin. Turns out that when you cool down matter very, very close to absolute zero, the topological properties of matter allow you to have a much more stable environment where you can work with these particles that we have discussed about. Hence, you get stable qubits. And just for our audience to understand, the biggest problem is keeping the qubits stable.
Right.
So in classical computing, it's very easy to keep a transistor stable, right? Because you use voltages, usually 0 or plus minus 5 volts, and that's very easy. That's you learn that in the 5th or 6th grade. It's basic physics. Now, keeping the state of a qubit, because the qubit works at a much, much lower physical level, is very, very, very difficult.
Let me break in.
And
you one of the things that people have to understand is 0 Kelvin, absolute zero, is negative 459.67 degrees Fahrenheit and negative 273 degrees, 0.15 degrees Celsius. So I just want to make sure we highlight the fact that we're talking about colder than anything in nature, including the vacuum of space. And that's why I wanted to just reiterate that.
yeah, and to go further with your example, the coldest places in outer space are around 3 Kelvin, 0 Kelvin being absolute zero. The typical temperature at which you aim to work with a quantum computer is around 30 millikelvin,
Right.
which is 100 times colder than the temperature of outer space. So even from this, you can imagine the difficulty of building those physical machines. Now, for those who are listening to us, let me say right from the beginning, it's not impossible.
No.
Right? Actually, folks have already done that, but it's very difficult.
Right. And so and I didn't mean to break your flow, but I think people have to understand that with all the quantum computing mechanisms that we've seen, every company, every country's approach requires these cold temperatures, because otherwise you're trying to it's trying to find a tear in the rain. There's just too much noise. There's too much at higher temperatures, you'd never be able to see the signal. There'd be too much jumping around. So that's where a lot of now Microsoft's approach, as you said, is using a different form of matter. And actually, since they seem like they're behind, if you really were looking at this out of the corner of your eye, you might think Microsoft is all just simulation. But if they're right, if their form of matter is what they think it's going to be, they should shoot right ahead. They should have much more stable and the ability to have many more qubits faster. And that's the bet, isn't it?
Yeah, I love that saying, there is no free lunch. And that applies. By the way, just as a side note, I have not yet seen a field, an area, a problem in computer science where this does not apply. So when building a quantum computer, it applies again. I mentioned about the players that are using superconductors or photonics or things that are in the same realm. Now, this is a relatively easier way to build the quantum computer. The price that you pay is that scaling up the number of stable qubits is very difficult. And as of today, you only have at most tens of stable qubits. And when I say stable, think about, in this world, stability means that a qubit is able to retain its state for a fraction of a second. So just to put things into perspective. Now, why Microsoft's approach is very promising is because using topological computing, the topological state of matter, the promise that this approach has is that once you build the first qubit, then scaling up to 100 or 1,000 or 10,000, it's just gonna be a problem of scaling your process, right? While with the other ones, it becomes more and more difficult. The more you add new qubits, it becomes increasingly difficult to keep their coherence, or as we say, to keep their state stable. So
Like a
that's
Jenga tower.
I agree with what you say, right? When Microsoft produces their first few stable qubits using topological quantum computing, they will be clearly ahead of the pack.
So we've covered a lot of ground. So we talked about why we need quantum computing, and we've probably just scratched the surface of that. We talked about what it is, but there's so much more to discuss on everything from Heisenberg principle of superposition, the double slit experiment, without making this a physics course. We talked about quantum versus classic, including why it's so hard to build a quantum computer. And we've just touched on who some of the players are and who to watch. Is there anything else we want to add before we top off this first episode? By the way, this first episode is meant to be a bit of a primer, but that's probably true of the first half dozen episodes that we plan.
Yeah, and I'd like to double down on what you said. We don't really want to have this podcast as a quantum physics course. No way. So what we're going to do is we're gonna break down some of these topics in future episodes, and we're gonna discuss them, and we're gonna try to help folks who are listening to us to understand that the principles, the high level approach, the concepts
Yep.
that are behind all this. The only thing that I would like to add is I mentioned there is a bunch of players who are trying to build the processors, but the actual number of players in the field of quantum computing is much larger. So there are close to 100 different companies or organizations who are today very, very active, whether they are in the actual computing field or in the networking or communications
Yeah.
or research or things like this, right? You mentioned one of those companies, and there are lots of other companies. Without any kind of preference, I would add here names like Airbus, Accenture, British Telecom, HP, Hitachi, and Intel. Yeah, that's a big one, and many others. So there's an increasing number of players. The ones that are actually kind of leading the pack in terms of building the thing are the ones that we have discussed.
Right.
Microsoft, IBM, Rigetti, Google, USTC, and D-Wave would be the most important names there.
Once we get through these introduction sessions, we'll start having guests from some of these organizations and talking about more topical news items that relate to this and what they mean. But first, we're trying to lay a good foundation.
I'm
Right.
so looking forward to that discussing with some of those folks. I've came to know a lot of them and discuss with them, and just as kind of like a preview. It's amazing having those people and discussing with them. So I'm really looking forward to those future episodes.
Me too. Me too. So I think that's all we have time for today. Any last words before we sign off this episode, Cyprian?
I would just like to say that it's I'm so happy and I'm grateful that I live to work and to perform my computer science career at this particular inflection point. We're so fortunate, Patrick, that we're actually living the moment when quantum computing is becoming a real thing. I can bet that 150 years from now, when historians will look back, will say, yeah, the 2020s were the years when a big breakthrough in computing happened.
Yep.
And back then, people named it quantum computing.
Yeah, I think it's going to be as big a change as the digital revolution. The fact that we have quantum fully usable by us is going to be as big a game changer as classical computing was when it first came out.
Fully
I think
agree.
that's all we have time for. Thanks for joining us, and we'll see you on the next episode of Entangled Things.